Hi again, welcome. This chapter is on the properties of light, optics. Now everyone loves a beautiful rainbow. A rainbow, like the one shown here, most people may not know, it's actually a perfect ring in the atmosphere. It turns out that we're usually only privy to see the top half of the rainbow, the part that does this. The lower half gets blocked off or chopped off by the horizon. Well, we can't see around the curvature of the earth, so we don't see the lower half of the rainbow unless you happen to be at just at the right altitude, right place at the right time. You can see much of the ring, so it's proof that it does have more of a ring shape to it than just an arched shape to it. Rainbows are quite fantastic. What causes a rainbow? Well, this is the chapter to find out. Things like the twinkling of stars, or the apparent twinkling of stars, they don't really twinkle, mirages in the desert, rainbows, how the human eyes work, fiber optic cables. This is a chapter that talks about all of these things. So many examples are dealt with. So in optics, we first start with an interesting property, or dual property, I should say. It's called a wave-particle duality of light. It turns out that all forms of electromagnetic radiation, the gamma rays and the microwaves, radio waves, ultraviolet, visible light, X-rays, they all they share a dual property. Sometimes they show properties of being a particle, actual mass, tangible, discrete mass, and sometimes they show properties of being a wave, something that's not really tangible, so to speak, and no mass to it. So which one's right, which one's wrong? Well, it just depends on how you're measuring it and the properties that ensue. It turns out that electromagnetic waves are both just that. They're actual particles, and which we now call photons, and actual pure energy, radiation. One of the experiments that's dealt with here is the Young's double slit experiment that proved the wave nature of light by a series of wave fronts that overlap each other and produce a series of light and dark bands over here on the detector screen. And so the reader will get the finer details of why this is and why it is a proof of the wave nature of light. And that's only one half of the story. The second half of the story is the particle nature of light. And for this, we call this the photoelectric effect, as Albert Einstein did. Arguably the greatest scientific mind to ever live, Albert Einstein. Some of the work he did, actually he published 5 papers around 1905 as part of his doctoral dissertation in physics from the University of Zurich. One of those won him a Nobel Prize in physics. It's the study of the photoelectric effect. It was definitive proof of the properties of radiation that the wave nature of light simply could not explain. And Einstein's work was able to do just that. One of my treks, I was in Europe. I was on a 10-country jaunt across Europe, and I was crossing from Liechtenstein, beautiful country out there across the Alps, into the city of Bern, one of the most beautiful cities in all of Europe, in my opinion, the city of Bern in Switzerland. And it's the city of Bern that I was wandering about, and I discovered in the actual city itself, I discovered this. And so, while you look a bit closer to the screen, let me just say your eyes don't deceive you. That one says the Einstein House and the other says the Schmuck Cafe. I'm not making this up. It's the Schmuck Cafe. Everyone's got to drink coffee, I guess. In any event, this is where Einstein lived in his mid-20s. In particular, in this Einstein House here, if I were to sort of scroll down, up here, well, down here, well, that's me enjoying my time there in Bern, getting a coffee from the Schmuck Cafe. I guess it was appropriate for me. On the 3rd floor here, right about here, this room made history. See, young Einstein worked as a patent officer, signing off electrical inventions here. And he lived up here in this 3rd floor. And it is in this room that changed the course of human history, on the 3rd floor up here. As a young man, Einstein, in his time, in his downtime, when he wasn't working in the patent office downstairs in the building, he he theoretically, he didn't perform these experiments. You know, he did thought experiments from his head, and many things came out of that one room. Arguably the world's most famous equation, E equals mc squared, the mass equivalence theorem, came out of that room. That's where he derived it. The special theory of relativity, which deals with things like length contraction in the direction of motion and time dilation. The further where you get from a gravitational field, time actually slows down. All of these things, these postulates for the special theory of relativity, was derived in that room on the third floor, right there. And it's also where he began his work on arguably his crowning achievement, the general theory of relativity, which deals with the curvature of space due to mass in a four-dimensional space-time continuum. All of that began right there in that one room. So in any event, if we zero down on one of those, the photoelectric effect, for which a Nobel Prize was given to Einstein, came out of that room, and it was definitive proof of the particle nature of light, what we now call a quanta, or a packet of light, a photon, and the photoelectric effect. Also in that town, by the way, as a caveat, there was a museum in there, and I discovered some real interesting things here. These are the handwritten notes of those papers that were eventually published of Albert Einstein himself. These are his handwritten notes as he was doing his derivations on the photoelectric effect. And the picture on the other side of it here, this is an actual report card from 1878, a high school report card from Albert Einstein. You can see all the subjects that he took and all the grades. I guess he was an okay student. I thought that was interesting at the museum. So the photoelectric effect, the reader will get much more detail on this, but in essence, only certain frequencies, energies of radiation that are impinging on an atom will cause the electrons to jump to higher energy levels or leave the atom altogether. That's the photoelectric effect. If the electrons don't receive a very specific quantity of energy, a quanta of energy that it likes, that is necessary for it to jump from one energy level to another within the atom, then it will simply not react at all. So in that respect, it has to accept a certain particle, that particle being a bundle or a packet of light, a photon, of a set amount of energy before the electron reacts. So this, in a nutshell, is the photoelectric effect. So much more detail was discussed here in the chapter on the photoelectric effect. So now that we've got those two things covered, the photoelectric effect, the particle nature of light, and Young's double slit experiment, the wave nature of light, proof of that, we can now look at some of the other properties and consequences of this wave-particle duality of light in this chapter. Reflection and refraction, for example, the different kinds of reflection, whether it's light is bouncing off a very smooth surface, that's called specular reflection, or the light is bouncing off a very rough surface, that's called diffuse reflection. That determines whether or not you're going to be able to see a very defined reflected image or not. Such things as incident rays, the normal reflected rays, and refracted rays are discussed when light enters a boundary between two different media. Some of the light is reflected away, but some goes into the new medium, the second medium. That's called a refracted ray. So many things are possible with this refracted ray, and much of it is discussed. This is known as Snell's Law. The refractive index of the first medium by the side of the angle of incidence of the first medium is equal to the refractive index of the second medium by the refracted angle, the sine of the refracted angle of the second medium. Again, the details are here in this chapter. But Snell's law is actually quite useful. It has applications in things such as the formation of rainbows. Light from the atmosphere, when it hits or light from coming in from the sun, for example, before it gets to the atmosphere, it goes from the effective vacuum of space to the atmosphere. And when it hits the atmosphere, it may go into some water molecules. And so once again, it goes from atmosphere to water molecules. It goes from a lower to a higher, what's called index of refraction. So as light goes from a lower to a higher index of refraction, the refracted ray gets bent closer to the normal. This is the normal that separates the, it's perpendicular to the interface of the two boundaries air and water, for example, a line perpendicular to that is called a normal, and all angles are referenced from this normal. So funny things and interesting things happen as light goes into different mediums, whether it gets bent towards or away from the normal will determine all kinds of things. For example, total internal reflection is one of them. And this is the foundation for fiber optic cables and the transmission, almost at the speed of light, of information. There are fiber optics cables. About 98% of all communication on Earth is done via fiber optic cables. And they cross mountains, they connect North America to Europe, thousands of miles of fiber optic cables are laid on the ocean floor, and this is how much communication is done. I mean, but 98% of all communication is done using fiber optic cables, and this is the basis of fiber optic cables. We discussed this in this chapter, so it's I think a very significant chapter. Much details are dealt with on the properties of light and radiation. Fiber optic cables only work if the light is going from a medium of higher index of refraction to a medium of a lower index of refraction. Why that is, well, the reader will find out in this particular chapter. I've also discussed the working of the human eye. The human eye is really a magnificent thing. It's barely an inch long, but yet the human eye can see the rings of Saturn, and Saturn's 1 billion miles away. So it's quite interesting. Well, not so much the rings, you need a telescope to actually see the rings, but to see the planet itself, it's 1 billion miles away. The human eye is quite fantastic. And so I look at what happens to light as it enters from air and goes through the cornea, the aqueous humor, and goes through the lens, and the vitreous humor, and eventually onto the retina. And the light bends multiple times. The human eye actually takes an image of an object that it sees, and on the retina it forms it upside down. It's the optic nerve that takes this signal and converts it right side up into the brain. So I explain how this works in this chapter. So this is the human eye, the diagram of it, and how it's constructed and how it forms an image. Twinkling of stars. Why stars appear to twinkle? That's also dealt with. It has to do with the different layers of the atmosphere. As the light comes from a star, it goes through the atmosphere, it hits different temperatures. Different temperatures of the air have different refractive indices, so it bends the light differently. As the light in a fraction of a second goes from the star to your eyes here, standing at the surface of the Earth, that light will bend several times as it hits different temperatures of the atmosphere on its way to your eyes. And that constant bending, which happens in a fraction of a second, gives the effect of a twinkling star. So the star doesn't twinkle, it's an aberration due to the different temperatures of the atmosphere. If you're ever lost in the desert and you think your salvation is close because you can see a mirage, and you get there and there is no such mirage, no such pool of water, that's how this happens. So I'm explaining how mirages happen here. It has to do again with the bending of light from the sky that bounces off the heated surface of the desert. The air directly above the sand is very hot, but the air above slightly higher is cooler. And that difference in refractive index of different temperatures causes the light from the sky to bend and to get to the viewer's eyes, and makes the viewer think that they're seeing an image of the sky, but at ground level. And that's what gives you the sense that you're seeing an image, a puddle of water. It's really an image of the clear blue sky, but the image appears to come from the ground. It's quite fascinating. Although that would be of no interest to a person who's actually stranded in the desert who really wants water. That would be a cruel joke. So this is what you would see typically in a desert. This is the Atacama Desert in Peru, one of the hottest deserts on Earth. I took a lot of water, as you can imagine, on my trip there. But mirages are very, very common in places like that where it's flat and it's very dry, very arid in the Atacama Desert. Talk about optical fibers and how they work. There's rainbows, how they're formed. Rainbow is actually a very complicated thing. It's quite complicated and quite complex, but I've explained it in great detail how significant rainbows are, and I think the reader will be amused by the fact that no two people on Earth can see the same rainbow. A rainbow is unique to the observer. Why that is? Well, you'll find out in the chapter. Well, this is taken in the west coast of Sweden. It's a rainbow. You can probably see a double rainbow. I've also explained why double rainbows are possible. There are actually many concentric rings that are rainbows, but the human eye is only sensitive to the first two, but there are many more. So I talked about reflection, refraction. Here I am in Guatapé, outside of Medellin, in Colombia, and I was on a boat, and I have a little device that lights up in contact with water. It fell out of my pocket and it fell into the bay, into this alpine lake over here. And so I could see the light coming out of the water, but it was being refracted away from the normal. So based on the refraction of the light, I was able to look at exactly where it was, so I can retrieve the light. So it was it made for a great example on the refraction and the reflection of light as it goes from different media, water and atmosphere. So that was actually pretty interesting. It wasn't fun at the time, but it's interesting now. Here's the solution to that problem of dropping my my light into the water and having to go get it back. This is the caves in Guilin in China, southern part of China. On my trips to the Far East, I toured this cave over here. It's quite a fantastic cave, and the play of light in that cave is just remarkable. I talked about the stalactites and stalagmites and how it creates shadows, which they're very elusive, these shadows, as they form. They seem to move as the water moves as well. Very interesting phenomena in those caves of Guilin. Here I am in Newfoundland in Canada, the Maritimes of Canada. Under these waters are fiber optic cables that connects all the way clear across the pond, the entire bed of the Atlantic Ocean, all the way to the coast of Ireland. I'm standing here on the coast of Ireland in Maidenhead, and under this rough-looking ocean waters are where the cables first started their journey all the way in Newfoundland over here. And so we did some calculations on the fiber optic cable and the propagation of light, the angle that the signal needs to enter into the fiber optic cable before it gets to the ocean floor, when the signal is sent in at Newfoundland before it gets to the station on the other side of the Atlantic Ocean. You know, we calculated what the angle of entrance needs to be, that incident angle. So it's quite a cool example. And as with every chapter, I've given several additional problems for the reader to gain some confidence in these types of problems. So I hope you found this interesting and helpful. Once again, I thank you for your time.